This is the question, the great question. Our universe began in a Big Bang. But why was there a Big Bang? How did everything begin? What was there before the beginning? Where did the material come from that created the Big Bang? What happened in the first instance to create that material? Why are we here? Strangely enough, some cosmologists believe a previous, cold, dark, empty universe, like the one which lies in our far future, could have been the source of our very own Big Bang. However, note that the only way to claim the universe was created from nothing is by waving a magic wand, full of confidence that people will go along with, because the universe was never truly empty, even before the Big Bang. Join us as we lift the veil on the origin of the universe. Here in our universe today, it's very clear that space is anything but empty. In every direction we look, we see stars, gas, dust, other galaxies, galaxy clusters, quasars, high-energy cosmic particles, known as cosmic rays, and radiation, both from starlight and leftover from the Big Bang itself. If we had better eyes, which is to say, superior tools at our disposal, we could also detect the signals that we know ought to be out there, but which cannot be detected with current technology. We'd see gravitational waves from every mass that's accelerating through a changing gravitational field. We'd see whatever is responsible for dark matter, rather than simply its gravitational effects. And we'd see black holes, both active and quiescent, rather than simply the ones that are emitting the greatest amounts of radiation. All of what we see isn't simply occurring in a static universe, but rather in a universe that's evolving over time. What's particularly interesting from a physical point of view is how our universe is evolving. On a global scale, the fabric of our universe, space-time, is in the process of expanding, which is to say that if you put any two well-separated points down in your space-time, you'll find that the proper distance between those points, the light travel time between those points, and the wavelength of the light that travels from one point to the other will all increase over time. The universe is not just expanding, but also cooling concurrently as a result of the expansion. As light shifts to longer wavelengths, it also shifts toward lower energies and cooler temperatures. The universe was hotter in the past and will be even colder in the future. And through it all, the objects with mass and/or energy in the universe gravitate, clumping and clustering together to form a great cosmic web. If you could somehow eliminate it all the matter, all the radiation, every single quanta of energy, what would be left? In a sense, you'd just have empty space itself, still expanding, still with the laws of physics intact, and still with the inability to escape the quantum fields that permeate the universe. This is the closest you can get, physically, to a true state of nothingness, and yet it still has physical rules it must obey. To a physicist in this universe, removing anything else will create an unphysical state that no longer describes the cosmos we inhabit. This means, in particular, that what we perceive as dark energy today would still exist in this universe of nothing that we're imagining. In theory, you can take every quantum field in the universe and put it into its lowest energy configuration. If you do this, you'd reach what we call the zero-point energy of space, which means that no more energy can ever be taken out of it and put to use performing some type of mechanical work. In a universe with dark energy, a cosmological constant, or the zero-point energy of quantum fields, there's no reason to infer that the zero-point energy would actually be zero. In our universe, in fact, it's observed to have a finite but positive value, a value that corresponds to an energy density of about 1 giga electron volt, about the rest mass energy of a proton per cubic meter of space. This is a tremendously small amount of energy, of course. If you took the energy inherent in a single human body, largely from the mass of your atoms, and spread it out to have the same energy density as the zero-point energy of space, you'd find that you occupied as much space as a sphere that was roughly the volume of the sun. In the very far future, Googles of years from now, the universe will behave as though this zero-point energy is the only thing left within it. The stars will all burn out. The corpses of these stars will radiate all their heat away and cool to absolute zero. The stellar remnants will gravitationally interact, ejecting the majority of objects into intergalactic space, while the few remaining black holes grow to enormous sizes. Eventually, even they will decay away through Hawking radiation. And that's where the story really gets interesting. The idea that black holes decay might be justifiably remembered as Stephen Hawking's most important contribution to science, but it holds some important lessons that go well beyond black holes. Black holes have what's called an event horizon, a region where once anything from our universe crosses over this imaginary surface, we can no longer receive signals from it. Typically, we think of black holes as the volume inside the event horizon, the region from which nothing, not even light, can escape. But if you give it enough time, these black holes will evaporate completely. These black holes evaporate because they radiate energy, and that energy gets drawn from the mass of the black hole, converting mass to energy via Einstein's E=mc². Close to the event horizon, space is more severely curved. Farther from the event horizon, it's less curved. This difference in curvature corresponds to a disagreement as to what the zero-point energy of space is. Someone close to the event horizon will see that their empty space is different from the empty space of someone farther away. And that's a problem because quantum fields, at least as we understand them, are continuous and occupy all of space. The key thing to realize is that if you're at any location outside of the event horizon, there's at least one possible path that light could take to travel to any other location that's also outside of the event horizon. The difference in the zero-point energy of space between those two locations tells us, as first derived in Hawking's 1974 paper, that radiation will be emitted from the region around the black hole, where space is curved the most strongly. The presence of the black hole's event horizon is an important feature, as it means that the energy required to produce the radiation around this black hole must come from the mass, via Einstein's E=mc² of the black hole itself. Additionally, the spectrum of the radiation is a perfect black body with its temperature set by the black hole's mass. Lower masses are hotter and heavier masses are colder. Of course, the expanding universe doesn't have an event horizon because it isn't a black hole. However, it does have something that's analogous, a cosmic horizon. If you're located anywhere in space-time and you consider an observer at another location in space-time, you'd immediately think, oh, there must be at least one possible path light could take that connects me to this other observer. But in an expanding universe, that's not necessarily true. You have to be located close enough to one another so that the expansion of space-time between those 2 points doesn't prevent emitted light from ever arriving. In our present-day universe, that corresponds to a distance that's approximately 18 billion light-years away. If we emitted light right now, any observer within 18 billion light-years of us could eventually receive it. Anyone farther away never would, owing to the universe's ongoing expansion. We can see farther away than that because many sources of light were emitted long ago. The earliest light that's arriving right now, 13.8 billion years after the Big Bang, is from a point that's presently about 46 billion light-years away. If we were willing to wait an eternity, we'd eventually receive light from objects that are presently as far away as 161 billion light-years. That's the ultimate limit. From any observer's point of view, there exists this cosmological horizon, a point beyond which communication is impossible since the expansion of space will prevent observers at these locations from exchanging signals beyond a certain point in time. And just like the existence of a black hole's event horizon results in the creation of Hawking radiation, the existence of a cosmological horizon must also, if the same laws of physics are to be obeyed, create radiation. In this case, the prediction is that the universe will be filled with extraordinarily low-energy radiation whose wavelength is, on average, of a size comparable to the cosmic horizon. That translates into a temperature of Haas 10 to 30 As. Kelvin, 30 orders of magnitude weaker than the current cosmic microwave background. As the universe continues to expand and cool, there will come a time in the far distant future where this radiation becomes dominant over all the other forms of matter and radiation within the universe. Only dark energy will remain a more dominant component. But there's another time in the universe, not in the future, but in the distant past, when the universe was also dominated by something other than matter and radiation during cosmic inflation. Before the hot Big Bang occurred, our universe was expanding at an enormous and relentless rate. Instead of being dominated by matter and radiation, our cosmos was dominated by the field energy of inflation, just like today's dark energy, but many orders of magnitude greater in strength and expansion speed. Although inflation stretches the universe flat and expands any pre-existing particles away from one another, this doesn't necessarily mean the temperature approaches and asymptotes to absolute zero in short order. Instead, this expansion-induced radiation, as a consequence of the cosmological horizon, should actually peak in infrared wavelengths, corresponding to a temperature of about $100 Kelvin, or hot enough to boil liquid nitrogen. What this means is that if you ever wanted to cool the universe down to absolute zero, you'd need to stop its expansion entirely. So long as the fabric of space itself has a non-zero amount of energy intrinsic to it, it will expand. So long as the universe expands relentlessly, there will be regions separated by a distance so great that light, no matter how long we wait, will not be able to reach one such region from the other. And as long as certain regions are unreachable, we will have a cosmological horizon in our universe, and a bath of thermal, low-energy radiation that can never be removed. What has yet to be determined is whether, just like Hawking radiation means that black holes will eventually evaporate, this form of cosmic radiation will fundamentally cause our universe's dark energy to decay away, too. No matter how clearly in your mind you're capable of envisioning an empty universe with nothing in it, that picture simply does not conform to reality. Insisting that the laws of physics remain valid is enough to do away with the idea of a truly empty universe. So long as energy exists within it, even the zero-point energy of the quantum vacuum is sufficient. There will always be some form of radiation that can never be removed. The universe has never been completely empty, and so long as dark energy doesn't decay entirely away, it never will be either. So after all, how did everything begin? What was there before the beginning? Where did the material come from that created the Big Bang? What happened in the first instance to create that material? Why are we here? The truth is, we don't know. But we can postulate physical and mathematical extensions to what's known to try to answer them. And under many of those extensions, there are indeed variations that are allowed. One of those possibilities is Kaluza-Klein theory and the birth of a multidimensional universe. Don't you know that even before Albert Einstein turned his famed brain to the theory of everything, his contemporaries Theodore Kaluza and Oscar Klein attempted to marry his theory of general relativity with James Clerk Maxwell's theory of electromagnetism, which in the late 19th century had provided an overarching explanation for the two main forces known at that time, magnetism and the electrical force. To make their theory work, Kaluza and Klein had to invent a world that looked very different from what we see around us. They had to add a fifth dimension to our three-dimensional space plus time. However, this fifth dimension was curled up and microscopic, a tiny loop that we cannot see on the level of everyday life. It was this theory that Einstein attempted to further develop into a unified field theory, which would describe all fundamental forces, including gravity, and the relationships between elementary particles in terms of a single theoretical framework without the need for quantum physics. His attempt ultimately failed. Since then, things have only gotten more complicated. Electromagnetism was superseded by the more complex quantum mechanics, which Einstein, according to reports, never fully accepted as it seemed too counterintuitive. Moreover, the number of dimensions of the universe needed for the evolving theory of everything to work has more than doubled. The first big breakthrough since Kaluza and Klein's 1920s theory came in the 1980s in the form of string theory. At that time, physicists, desperate to get rid of the infuriating infinite values produced by the theoretical colliding graviton particles, proposed that elementary particles of the microcosmos perhaps weren't simple points in space, but instead tiny loops of strings which only appear point-like to us. According to this theory, as the strings vibrate, twist, and fold, they produce effects in many tiny dimensions that humans interpret as everything from particle physics to large-scale phenomena like gravity. Renowned as a possible theory of everything, string theory is a framework that physicists use to describe how forces usually conceptualized on a gigantic level, like gravity, could affect tiny objects like electrons and protons. In Albert Einstein's theory of general relativity, gravity is a force that warps space-time around massive objects. It's one of the four forces that physicists use to describe nature. But unlike the other forces, electromagnetism, the strong force, and the weak force, gravity is so weak that it can't be detected or observed on the scale of a particle. Instead, its effects are only noticeable and important on the scale of moons, planets, stars, and galaxies. Gravity seems not to exist as a particle of its own either. Theorists can predict what a gravity particle should look like, but when they try to calculate what happens when two such gravitons smash together, they get an infinite amount of energy packed into a small space, a sure sign that the math is missing something. One possible solution, which theorists borrowed from nuclear physicists in the 1970s, is to get rid of the idea of problematic, point-like graviton particles. Strings, and only strings, can collide and rebound cleanly without implying physically impossible infinities. String theory turns the page on the standard description of the universe by replacing all matter and force particles with just one element: tiny vibrating strings that twist and turn in complicated ways that, from our perspective, look like particles. A string of a particular length striking a particular note might gain the properties of a photon. Another string folded and vibrating with a different frequency could play the role of a quark, and so on. In addition to taming gravity, string theory was attractive for its potential to explain so-called fundamental constants, like the mass of an electron. The next step, theorists hoped, would be to find the right way to describe the folding and movement of strings, and everything else should have followed. But that initial simplicity turned out to come at the cost of unexpected complexity. String math didn't work in our familiar 4 dimensions, 3 of space and 1 of time. It needed a total of 10 dimensions, with 6 visible only to the perspective of the little strings, much as a power line looks like a 1D line to birds flying far overhead, but becomes a 3D cylinder to an ant crawling on the wire. By suggesting a multitude of different recipes for space-time, the fabric of the universe, string theory helped originate the multiverse concept, a theory of alternate universes alongside ours, which may possess different physical laws than the universe we live in. Our universe is unimaginably big. Hundreds of billions, if not trillions, of galaxies spin through space, each containing billions or trillions of stars. Some researchers studying models of the universe speculate that the universe's diameter could be 7 billion light-years across. Others think it could be infinite. But is it all that's out there? Science fiction loves the idea of a parallel universe, and the thought that we might be living just one of an infinite number of possible lives. Multiverses aren't reserved for Star Trek, Spider-Man, and Doctor Who, though. Real scientific theory explores and in some cases supports the case for universes outside, parallel to or distant from but mirroring our own. Multiverses and parallel worlds are often argued in the context of other major scientific concepts, like the Big Bang, string theory, and quantum mechanics. Eternal inflation. the Big Bang Theory, and parallel universes. Around 13.7 billion years ago, everything we know of was an infinitesimal singularity. Then, according to the Big Bang Theory, it burst into action, inflating faster than the speed of light in all directions for a tiny fraction of a second. Before 10 to the power of -32 seconds had passed, the universe had exploded outward to 10 to the power of 26 times its original size in a process called cosmic inflation. And that's all before the actual expansion of matter that we usually think of as the Big Bang itself, which was a consequence of all this inflation. As the inflation slowed, a flood of matter and radiation appeared, creating the classic Big Bang fireball, and began to form the atoms, molecules, stars, and galaxies that populate the vastness of space that surrounds us. That mysterious process of inflation and the Big Bang have convinced some researchers that multiple universes are possible, or even very likely. According to theoretical physicist Alexander Vilenkin of Tufts University in Massachusetts, inflation didn't end everywhere at the same time. While it ended for everything that we can detect from Earth 13.8 billion years ago, cosmic inflation in fact continues in other places. This is called the theory of eternal inflation. And as inflation ends in a particular place, a new bubble universe forms. Those bubble universes can't contact each other because they continue to expand indefinitely. If we were to set off for the edge of our bubble, where it might butt up against the next bubble universe over, we'd never reach it because the edge is zipping away from us faster than the speed of light and faster than we could ever travel. But even if we could reach the next bubble, according to eternal inflation, combined with string theory, our familiar universe, with its physical constants and habitable conditions, could be totally different from the hypothetical bubble universe next to our own. In the words of Vilenkin, this picture of the universe, or multiverse as it is called, explains the long-standing mystery of why the constants of nature appear to be fine-tuned for the emergence of life. The reason is that intelligent observers exist only in those rare bubbles in which, by pure chance, the constants happen to be just right for life to evolve. The rest of the multiverse remains barren, but no one is there to complain about that. Vilenkin's explanation implies that in some of the infinite bubble universes outside our own, there could be other intelligent observers. But in every instant that passes, we get farther away from them, and we will never intersect. Quantum mechanics and parallel universes. Some researchers base their ideas of parallel universes on quantum mechanics, the mathematical description of subatomic particles. In quantum mechanics, multiple states of existence for tiny particles are all possible at the same time. A wave function encapsulates all of those possibilities. However, when we actually look, we only ever observe one of the possibilities. According to the Copenhagen interpretation of quantum mechanics, as described by the Stanford Encyclopedia of Philosophy, we observe an outcome when the wave function collapses into a single reality. But the many worlds theory proposes instead that every time one state or outcome is observed, there is another world in which a different quantum outcome becomes reality. This is a branching arrangement in which instant by instant, our perceived universe branches into near infinite alternatives. Those alternate universes are completely separate and unable to intersect. So while there may be uncountable versions of you living a life that's slightly or wildly different from your life in this world, you'd never know it. The many worlds theory is the most courageous take on the quandary of quantum mechanics. Physicist Sean Carroll wrote in his book, Something Deeply Hidden: Quantum Worlds and the Emergence of Space-Time. He also argued that it is the most straightforward theory, although not without wrinkles. One of those wrinkles is that the many worlds idea is not really falsifiable. This is an important component of scientific thought and is the way the scientific community develops ideas that can be explored with observation and experimentation. If there's no opportunity to find evidence against a theory, that's bad for science as a whole. Infinite space, infinite universes. Some physicists believe in a flatter version of multiple universes. That is, if the universe that we live in goes on forever, there are only so many ways that the building blocks of matter can arrange themselves as they assemble across infinite space. Eventually, any finite number of particle types must repeat a particular arrangement. Hypothetically, in a big enough space, those particles must repeat arrangements as large as entire solar systems and galaxies. So, your entire life might be repeated elsewhere in the universe, down to what you ate for breakfast yesterday. At least, that's the theory. But if the universe began at a finite point, as nearly every physicist agrees that it did, an alternate version of you likely doesn't exist. According to astrophysicist Ethan Siegel, the number of possible outcomes from particles in any universe interacting with one another tends towards infinity faster than the number of possible universes increases due to inflation. So what does this mean for you? It means it's up to you to make this universe count. The mirror image universe. In a relatively recent addition to the pantheon of multiverse theories, researchers from the Perimeter Institute for Theoretical Physics in Waterloo, Ontario, have proposed that the universe began at the Big Bang, and on the opposite side of the Big Bang timeline, stretching backwards in time, a universe once existed that was the exact mirror image of our own. Imagine cracking an egg in this anti-universe. First, it would be made entirely of negatively charged antiprotons and positively charged anti-electrons. Secondly, from our perspective in time, it would seem to go from a puddle of yolk to a cracked egg to an uncracked egg to inside the chicken. Similarly, the universe would go from exploding outward to a Big Bang singularity and then exploding into our universe. But seen another way, both universes were created at the Big Bang and exploded simultaneously backward and forward in time. This dichotomy allows for some creative explanations to problems that have stumped physicists for years. For one, it would make the first second of the universe fairly simple, removing the necessity for the bizarre multiverses and dimensions experts have used for 3 decades to explain some of the stickier aspects of quantum physics and the Standard Model, which describes the zoo of subatomic particles that make up our universe. In addition, this theory would offer a much simpler explanation for dark matter. The scientists say this new theory grew out of a dissatisfaction with the bizarre add-ons proposed by physicists in recent years. What's interesting, they also say this new theory has the benefit of being testable, which will be crucial in winning over doubters. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.